So hi all. For those of you who don't know me, I'm Leo. I was just graduated from Penn, and I've been working on QuickCheck. And today we're going to talk about TIMP. We're going to put types into the IMP language that you might have seen in Software Foundations. So regular IMP had this feature where we had two distinct namespaces for arithmetic and Boolean expressions. And in fact, variables were only allowed in arithmetic expressions. That is very convenient if you are proving things about a language, but very inconvenient when using it. So the goal of this case study is to collapse the two grammars, have one type of expressions, allow variables to range over both, and then introduce types to keep things sane. When we're doing that, the soundness property of TIMP, that well-typed programs cannot go wrong, is a perfect example of a good, realistic conditional property. Benjamin was talking yesterday about how when you have a conditional property, you might have to put more effort into your generation to make it better. And that's exactly what we're going to see today. But to begin with, let's give an overview of TIMP and what we're going to talk about. Identifiers. Identifiers for TIMP are going to just be natural numbers. Here I've just defined a wrapper around it so that we are able to play with type class instances a bit better. But literally, identifiers just natural numbers. We're going to need one identifier specific operation. That is fresh. Okay. Fresh, whenever we want to deal with variables, if we have a set of variables, we might want to be able to generate a fresh ID given a set of already existing identifiers. Since our identifiers are natural numbers, we can just do that by taking the identifier that is one more than the max of a set. That is an easy way of getting fresh. We'll also need to be able to decide the equality between identifiers, and Benjamin yesterday already showed how to do that with DEC-ACK, so I'm going to gloss over that fact. And we'll also obviously want to print and generate identifiers. Printing is easy. We can just give a show instance based on the show instance for NAT, just wrapping it around. And to generate identifiers, we have a choice. We have our first choice. We could just generate arbitrary natural numbers and produce identifiers through that. But that way is not actually what we're going to need. Whenever we have a context of already existing variables, it's highly likely that we're going to want to pick one of those variables to start playing with. If you have a variable that you've already assigned to, you're much more likely to want to keep using it. So instead of just generating an arbitrary identifier, our generation is going to be this function is a way of generating a list of identifiers of a specific size. So we just keep generating fresh identifiers based on that list. And we end up with n identifiers at the end. To pick from one of those, yesterday Benjamin introduced the elements combinator. And I think there's a small exercise here about putting the two together. But it's something we can use. Types. This is the very, very confusing type of types in TIMP. It has Booleans and natural numbers. That's it. Nothing fancy. I've been hearing a lot of complaints this morning about how a lot of the stuff we made you do yesterday in the exercises are tedious and only worth it if you actually have a big development. Well, you don't actually need to do almost nothing that was in the exercises yesterday. QuickCheck does it for you. So here you can derive arbitrary and show for tie, and you can generally do this for any simple inductive type in Coq, like trees, lists, whatever. You can just use this deriving mechanism, and you'll get the show and generator and shrink instances for free. So, yeah. It is useful to know how to write those things manually for when things go wrong, but for 99% of your situations, you could use this. Decidable equality. Again, this is exactly what we've seen for everything else. We just need to be able to decide when two types are equal, and we use the DEC-ACK tactic to do that. another decision. At some point, we're going to need to encode typing environments and later on states. So we want to have some sort of map from our variables, from our identifier to either types or values or anything. And for those of you that are familiar with software foundations, there is already such a map functionality in the first or second volume. But there is a tiny problem. It uses a function-based representation. So we represent a map in logical foundations with a function. For proving things about it, that is actually perfect. But if you want to use it for testing, it becomes slightly more inconvenient. Why? Well, think about what you would want to do with a typing context here in testing. You would want to be able to test if two typing contexts are equal. You want to be able to access the domain of the map so that you can iterate over it and like print it or generate new things based on it. So, and those operations are not really easy to implement for a function. Yes, you could do something if the function has a finite domain, like if you restrict all identifiers to be the 26 characters, and that would probably have been enough for this example. But for any realistic example, a function-based representation for a map is probably not going to cut it. So when testing, that's often something you have to take into consideration. You want to be able to reify your data structures in order to be able to print or generate them or play with them in general for testing. So for this purpose, we're going to use a simple list-based representation. Just an association list, and we're going to need 4 operations. Empty, the empty map, get to look up an element, set to look up to set the binding of an element, and DOM to get the domain of the map, to get the set of keys of it. These are pretty obvious, so I'm going to go through them slightly fast, but ask if anything is off. We have the empty map, which is just the empty list. We have a get, which is just iterating through the map until we find an identifier, a key that is equal to the identifier we're looking for. And I want to point out here that we don't impose any invariant on the map. We don't impose that the list is sorted on keys. We don't impose that everything is distinct or anything like that. We just allow shadowing, and we allow the binding of a variable to override later occurrences. So you can just keep duplicates, and the one that matters is the first iteration in the first appearance of an identifier on the list. And we can use that to our advantage so that the set is just a cons. So in order to update the binding of an element, no matter if it's already in the map or not, you can just set it in front. And the domain of the keys is obviously just the set of the first components of the pairs. Okay. Now I'm going to do something that does not appear necessary. I'm going to introduce a relation that wraps around the get function. The reason I'm doing that is to talk a bit about automation at the very end of the lecture, but it's also good to present things a bit better. So here's an inductive relation bound to. It holds for a map M, an identifier X, and some element A, if the binding of X in M is equal to A. So that's all this bound to does. Every time we have an inductive relation, it's very likely that we're going to want to compute with it and decide it. So we want to be able to decide whether bound to MXA holds for the given triplet. And in the volume, you can see the full proof of this. It's not actually hard, but it's not actually the purpose of the current talk. So there is an optional mini chapter here about how to automate these kinds of proofs. Feel free to ignore it on the first reading. Feel free to look into it and give us comments if you have any. So let's actually use our maps. We're going to use our maps first to represent typing contexts. Typing contexts are just a map from identifiers to types, so that's how we instantiate the parametric parameter in map. The operation we're going to want is to generate an identifier of a given type given a context. So if we're given a context gamma and a type tie, we want to be able to generate an identifier that has a specific type. However, that is not always possible. Maybe the map is empty. Maybe the context only contains booleans and we want to generate a natural number. So for that reason, it's customary for all generators that for such conditional properties, if we want to generate an identifier such that bound gamma x t holds, it's highly likely that we want to convert our result type to a generator for options of identifiers to signify failure. Okay, how are we going to generate identifiers? The easiest way would be to filter the list to keep only the elements that have the type that we want, and then just return the identifiers from it. However, as I said, that result of the filter might be empty. So that is where the default element of one-of comes in. Yesterday there was a short discussion that I said there will be an example where we want the one-of with a lowercase o instead of capital O that takes a default element. And this is why we don't want to throw an exception here. You can use the default element to be none. You can return nothing in the default case. But if the result of your filter is not empty, the none will be ignored. So that's a very common idiom that arises when you're doing any sort of manipulation with conditional things. Generating typing contexts. This is also fairly straightforward. We want to be able to generate a context with a specific size. To do that, we just generate a bunch of fresh identifiers with a function we defined earlier, then generate an equal number of arbitrary types and zip them together. You'll note that this doesn't generate any duplicate elements in the context, and the result will actually be sort of sorted. So it doesn't actually generate all possible contexts that we would be interested in. But for our present purposes for this chapter, this is probably enough. Okay, any questions so far before I go to expressions? Good. Expressions in TIMP. In the original IMP, there's a line drawn here. So everything on top has to deal with arithmetic expressions. We have numbers, plus, minus, and multiplication. Everything below is booleans: true, false, equality tests, and negation and conjunction. Also in IMP, variables were only allowed to range over arithmetic expressions. So now that we've collapsed it to syntaxes, there is no such distinction. So our variables here are going to represent arbitrary expression, not just integers. And again, you don't have to write the annoying instance of show by hand for such a thing. You can just get the show function. And while that is not always what you want, we're not going to pretty print an expression like this, it's a very good start. So a very common way of going about testing a small to medium development is derive everything, and the moment things start to be a bit out of hand, like, okay, I have this show instance that I got from QuickChick, but when printing numbers, I don't want to say enumn, I just want to show the natural number. So you go in and customize the show instance a bit. But it's a good place to start, as we're going to see. Okay, this is arguably the first interesting slide of this talk. Typing for TIMP. This is something that we didn't see in any version of IMP. If you're following along in the volume, you'll note that the notation that we have there is hideous. I changed it to Unicode for the purposes of the presentation, but we're not sure if we're going to do that in the actual chapter. So what are typed expressions? The relation has type holds when a context gamma, when an expression in a context gamma has the type tie. Most of these cases are fairly straightforward and exactly what you'd expect. Numbers are always natural numbers. Boolean constants always have type bool. For plus, if you have an expression, two expressions that are of type nat, then their addition is also of type nat. Subtraction and multiplication work the same way. Equality tests work the same way. And the only case that works slightly differently is the tyvar case. So for a variable to have a specific type, we need x to be bound to tau in gamma. Okay. Any questions so far? Let's keep going. Once again, we want to be able to decide whether whether an expression has a given type. Here we have just a decidable instance for that relation. It's not necessary to write this in a decidability proof sort of way anymore in QuickCheck. You can just give a short function that decides it and play with different type classes. But for now, let's just give a decidability instance. Once again, there are a few details about proof automation in the proof part of this thing in the volume, but you can feel free to ignore it on the first reading and focus on the testing. Good. So what we're going to need in this talk is to be able to generate typed expressions. So there is a way that we can there is a way of getting it easily, and that is generate arbitrary expressions and filter them using the decidability instance for has type. That is not going to work. Just think about how many ways you can go wrong. You could try adding booleans. You could try negating a natural number. You can use a variable in a context as both an integer and a natural number and a boolean. There are just so many ways that it can go wrong that generating well-typed expressions instead of by generating arbitrary expressions and filtering them is extremely inefficient. So, as Benjamin pointed out yesterday, it's very common for writing a conditional generator, writing a custom generator that returns an element of the specific precondition, here, typed expressions, directly. And like before, we're going to wrap the result in an option because it's possible that our generation will fail. Think about it, because not every combination of inputs could result in an expression that is well typed. So, sorry. We're going to introduce a different bind because the option variants of the G are less convenient to work with if you have to do this every time. So what we have here is a bind for the G opt monad. So first we will get out an optional A, match on it. If the optional generator had failed, we just fail again. But if it has some content and has produced an A, we can use it to chain it together with our continuation. In fact, this is so common that QuickCheck introduced explicit monadic notations for it. We have a G opt monad, which is literally just G of option of A. And there is a monad instance for it, so you can use the beautiful notations that xlib introduces. Okay, that brings us to our first interesting generator. That is one for typed expressions. Instead of giving you the huge generator that is produced directly, I'm going to build up to it from simple examples that are dealing with a few of its constructors at the same time. So the first relation I'm going to introduce is going to be has type 1, which is literally just the first constructor of the has type relation. We start with variables, and the variable has a specific type if the identifier is bound to tau in gamma. Now, in order to satisfy this relation,